Honors Physics, homework problem number 21, day 153. Magnetic force between wires. Here we have 4 wires that are like posts sticking out of the ground, carrying currents as indicated. 2 of the currents are toward the floor, the X's, and 2 of the currents are toward the ceiling, the dots. The one on the lower left is also 16 amps. They're all 16 amp currents. This one got cut off over here in the corner. 16 amps in all 4 wires. Each pair of wires exerts a force on each other. Let's just pick one corner because the answer is the same on all 4 corners. Solve this problem in one corner, it applies to all 4 corners. Let's take the lower left corner. The 2 bottom wires have currents in opposite directions, and the rule is if the currents are in the opposite directions, they repel each other. The way we can show that on the diagram here is this wire is being forced that way. They're both repelling each other with equal forces. I'm just going to call that F sub 1 and F sub 2. F sub 2 doesn't really matter, but they come in pairs. And then on the left-hand side, those 2 wires, top left and bottom left, also are repelling each other. I can show you that with vector arrows. Call that, well, let's call it F4 and call this one F3. All 4 of those will be equal magnitude because we have the same currents in all the wires and we have the same distances. I can calculate those. F sub 1 will equal F sub 2 will equal F sub 3 will equal F sub 4. I don't really care about number 2 and 4, but just to be thorough here. And the equation is our constant 2 times 10 to the negative 7th times the current in each wire, 16 times 16, which would be 16 squared, times the length of the wires. That was given in the problem. The length of the wires are 1.25 meters, divided by the separation between the wires in meters, which is 0.025 meters. That's how far apart they are. So all 4 of those forces have a magnitude of 2.56 millinewtons. Now the other pair of wires, the ones that are diagonal from each other, lower left, upper right, those 2 wires have currents in the same direction, so they attract each other. I'll switch to blue. So this wire and this wire attract each other, and that force is going to be a little bit smaller because of the greater distance, but I'll call that F sub 5, F sub 6. Don't really care about F sub 6, but once again, just to be thorough, I have both those on there. And this would apply to all 4 corners once again, but I'm just focusing on this lower left-hand corner. I will calculate F sub 5, which is equal to F sub 6, which is 2 times 10 to the negative 7th, times the 16 squared, times their length, still the same length wires. But that distance now is not 2.5 centimeters. It's the diagonal distance across the square. And you could use Pythagorean theorem to figure that out. You can show the work for that. But bottom line is just going to be basically 2.5 times the square root of 2 as the distance. Or, yeah, well, so 2.5 centimeters. 2.5 times the square root of 2 comes out to be 3.53 centimeters as the distance across from corner to corner of that square. So in meters, that's 0.0353 meters. So our force goes down a little bit. It goes down to roughly 1.81 millinewtons. All right, now in that corner, I have a vector problem, which is not that difficult because we can take some shortcuts here like this. What I'm noticing is that, well, I know that the F5 that I just calculated, F sub 5, is at a 45-degree angle, which makes me first think, well, I got to find the components of F sub 5. However, there's a shortcut here. If you look at F sub 3 and F sub 1, which are the same magnitude, if I add those first, they result in a vector at 45 degrees opposite the F sub 5, but lined up with it. So for example, if I simply just look at the F sub 1, which is to the left, and F sub 3, which is down, those are both the 2.56 millinewtons, 2.56, 2.56. right? Well, they result in this vector over here. I'll just call it r. Well, r is just going to be the 2.56 times square root of 2, and it will be a 45-degree angle because it's an isosceles triangle. And you can just show the diagram there and just do that off to the side. So r comes out to be 3.61 millinewtons. And since now that r, 3.61 millinewtons, lines up with f sub 5, because they're both at 45 degrees but opposite direction, simply all we need to do is subtract those two. The bigger one is the 3.61. So I take the 3.61, these are all millinewtons, minus the 1.81 millinewtons of f sub 5 in the opposite direction. That gives me 1.80 millinewtons as my magnitude of the final answer, with a direction of diagonally outward. I'll just say that, diagonally outward. With respect to the square. So that's my answer for all four corners. If that's the answer for one corner, it's the answer for four corners, because this is a very symmetric problem. All four corners have the same currents with the same scenario. So all four wires have that force diagonally outward.